All right, here we are in Calculus 30. We find ourselves at section 2.7. We're going to talk about implicit differentiation. So we've talked about all the differentiation rules. We've taken all sorts of functions and we've applied the constant multiple rule, the constant rule, the sum difference rule, the product rule, the quotient rule, the chain rule, all those kind of fancy rules to find the derivative of an equation. Now we're going to approach things just a bit differently because there are all sorts of types of equations out there. Now, implicit differentiation, let's talk about the word implicit first of all. You may have heard this word before. Implicit means it is implied. So it's from the root word implied, meaning that it's not plainly expressed. Maybe you've heard of the other term, the antonym there of explicit. Have you heard of explicit? Usually that's kind of a negative thing, right? Oh, explicit lyrics or explicit sexual behavior or something like that. This is where you've maybe heard these words. And this is like not implied, it's very plain, like it's very kind of raw, okay? But implied is something that's a little more, I wouldn't say subversive, but it's a little more under the surface, right? So in mathematics, implicit means not expressed directly in terms of independent variables. So let's take a look. So far, we've described functions by expressing one variable in terms explicitly in terms of another, okay? So for example, these are examples that you'll see, like y is on the left side of the equation, and all of the other stuff, including the x term, is on the right side of the equation. That's what we mostly see. Here's another one. Y and x are separated by the equal sign, okay? Y is expressed explicitly in terms of x, okay? But other functions, such as this one right here, x squared plus y squared equals 25. Does anyone know offhand what this would graph if we were to graph all of these points, x and y? Yeah, unfortunately in high school we don't study circles much. The conic sections, we took that out of the curriculum for whatever reason. That's now done in post-secondary. But we used to study functions of conic sections. And we still do study parabolas, which is a conic section. We used to study hyperbolas and ellipses and circles. This is the equation of a circle. So this is a circle with the center at the origin, radius 5 units. Okay? But what we want to learn from this is that this is an example of an equation where y is not explicitly expressed in terms of x, right? Y is not on one side of the equation and x on the other side. They're both on the same side. And so in this case, we could rearrange this equation so that we could isolate for y and have y on one side and only terms, including the x on the other side. We could do that. We could take the x squared over, so 25 minus x squared. We could take the square root of the whole lot. And then we have two separate equations, really. When you take the square root of something in the process of solving something in a math equation, you have to consider both the positive and the negative options there. So really, we get two explicit equations here. And you can kind of see that this one single equation and these two are quite different. And with the radical, with the root sign in here, it makes it a little trickier to do calculus on it. And so what this is, as I mentioned, the complete equation down here is a circle. Okay, all the points that would fit into this equation map a complete circle. But notice it's not a function. The circle is not a function. So y is not a function of x here. If we were to do that, y expressed as a function of x, or explicitly in terms of x, we would only be able to graph 1/2 of the circle at a time. Remember the test for functionality there, if it's a function, it'll pass the vertical line test, right? So this is, on the left here, this is not a function because it does not pass the vertical line test, touches twice. So not a function, y is not a function of x. But these are functions. Notice the term, the notation. This is function notation. Okay, what's the whole point? Well, the whole point is that implicit differentiation, what we're studying today, does not require a separation of variables. And so this equation right here is actually pretty easy to separate the variables, but in a lot of equations, it is nearly impossible to separate the variables. And being that that's so difficult to separate the variables, the differentiation, or differentiating the resulting equation or equations there, would be even more difficult. So there must be another method to avoid having to separate the variables, and that is what we're studying today, implicit differentiation. So if you're jotting down some notes here, implicit differentiation does not require a separation of variables, okay? And that's because in most cases it's very difficult to do that, and it's even more difficult to differentiate. Instead, what we'll do is we'll focus on a few key principles here, okay, in order to differentiate an equation. So number one, when differentiating with respect to x, which most of the questions will be, dy dx, or differentiate with respect to x, there's going to be one preferred variable, and I call it a preferred variable. You'll hear me use that terminology. The preferred variable would be x, so differentiating with respect to the preferred variable x. We have to remember that x prime, or the derivative of x, equals 1 when we are differentiating with respect to x. But when we differentiate y with respect to x, y prime equals y prime. And that might seem really obvious because that's what we've been doing the whole time. Watch this. If we have y equals 2x squared plus 1, the derivative of y is what? Well, y prime. That's what we do. And the derivative of this side is 4x. Okay? And then times the chain rule, what's the derivative of x? 1. Okay? So we've been doing this all along, but we haven't really noticed. Now, if you have y mixed up in the equation, when you take the derivative of y, it's going to be y prime. You have to write it as y prime, or dy dx. We will use the Newton prime notation mostly because it's the less confusing, I think. The other thing we want to remember is we use the differentiation rules just as we normally would, like all of the rules I mentioned earlier. But especially we want to focus on the chain rule. You need to think about the chain rule when you're doing implicit differentiation. And you need to think about the chain rule for every single term. And that'll become more obvious as we go through some examples. So those are a couple things we want to remember at the outset. Let's differentiate the first example, this circle equation. Let's differentiate this implicitly. So we are not going to separate y all by itself and do two equations. We're just going to do one. And if we remember these two things and to think about the chain rule for every single term, you're going to be just fine. Now this is going to look weird, okay? You ready for this? This is going to look really weird, different than what we've done before. But let's tackle each term separately. So the first term is the x squared. Now, does this contain the preferred variable here? Yes, it does. Okay, so we're going to differentiate this as we regularly would, just regular old differentiation. That's going to be 2x, okay? So again, I'm taking the derivative here of this whole equation. So that equals 2x for this first term, okay? Everybody get that? Just normal. Now, here's where it gets tricky. The derivative of y squared. Now, if you think about the chain rule, I have a quantity squared. Exactly the same as I had with the first term, a quantity squared. So I'm going to think about the outside function, that is the quantity squared part. The inside function is the y itself. So I do chain rule. Outside function is going to be 2. Now I don't differentiate what's inside first, do I? I do 2y to the power of 1. I'll write this out so you can see what I'm doing. And now, because y is not the preferred variable, the chain rule, which over here, the derivative of x was 1. Here, the derivative of y is y prime. Okay? So that's the difference. You see, chain rule over here, the derivative of x is 1 multiplied by 1. The derivative of y is y prime. So this is the big deal right here. This is the big deal. Okay, because we've always had y just by itself, so we've always just focused on y prime. What's the derivative of y? Y prime. Well, now we're going to have, like, y is going to be mixed up in other terms with other variables and with exponents and in the denominator. Okay, so you got to think about this as chain rule now. All right, what's the derivative of 25? 0. Very good. That's still the derivative of a constant is 0. Okay, so now where do we go from here? This looks like a real mess, doesn't it? This is a real mess, but not really. Because what are we looking for? We're looking for the derivative with respect to x, or this is also, I'll write it over here, dx of this. So we're really looking for y prime. That's what we're trying to solve for, okay? And here, now what you look at, now this is where you separate your variables now, in a sense. You separate the y prime by itself, because that's what we're actually looking for. And believe me, this is much easier than separating the variables for the original one, because usually we kind of like, I don't know, it seems like we whittle down the big equation when we differentiate it a bit, and then there's only one thing you have to solve for here, and I don't know, it's a lot easier to solve now for y prime at this point than to separate at the beginning in most cases. So, yeah, we won't put that equal sign at the front. That's premature. So don't do that. The equal sign is over here. Because we're gonna differentiate it as a whole. So now I subtract 2x from both sides. Okay, regular algebraic manipulation here. 2y prime equals negative 2x. And I'm going to get y prime by itself, so I need to divide both sides by 2y. And so y prime now is all by itself, and I simplify the right side, and I get negative x over y. All right? And here is the second thing that you will find. Okay, the second note here. Okay, in implicit differentiation, you will see that y prime will be in terms of x and y. Okay, that's a general statement. I think that happens all the time. Yeah, you're gonna have it's gonna have x and y on the other side. All the times that you'll see, I believe. So in implicit I'll write this word out. In implicit differentiation, you will see that y prime will be expressed in terms of both x and y. Okay? All right, so take a look at that. Do you have any questions about that? Any thoughts about that? Anything that like is just not clicking, not making sense right now, you want to clarify? No? Okay. All right. So let's keep going. Let's do another one. This one's a little bit more difficult here, but what we have to remember is that we are just going to have to use all the rules that we have learned this chapter. So we're going to have to remember the sum difference rule, the power rule, the product rule, and of course the chain rule in this one. So go ahead and take a second to write that down. Find dy dx if 2x to the 5 plus x to the 4th y plus y to the 5 is 36. Okay, so again, we're going to focus on each term separately, each term that we see. We're not going to move anything around, first of all. We're going to just attack the first one first. So this is an x term. Nice. This is like old times, okay? So this is 10x to the 4th. Done. Move on. Okay, awesome. Now this one here is a product of two functions, that is x to the 4th and y. So I have to use my product rule. All right, so the derivative of x to the 4th is 4x cubed. Got that? And in the product rule, I want to do the derivative of the first times the second. So this is a regular old y here. And let me just highlight this in blue. Okay. So 4x cubed y plus, let's just do this separately, plus the first, x to the 4th, times the derivative of the second. The derivative of just y is y prime. Okay. All right, so first time you've seen this implicit product rule in action here, take a moment to digest that. Derivative of the first times the second plus the first times the derivative of the second. Okay, you liking that? I mean, you okay with that? Making sense? All right, let's move to the next one. So plus, now this is not the preferred variable, so I have to remember chain rule. Okay, got to remember chain rule. Outside function, 5y to the 4. That's the first outside part. The inside part is the y itself, so we need to multiply by y prime. Equals the derivative of a constant is 0. Okay, first step of differentiation, first step of implicit differentiation. How are we feeling about this one? Okay? Yes, question?
Do we only have to use chain rule when the y is like separate?
Well, you use chain rule every time, but the derivative of x itself is just 1, so it's times 1 at the end, right? So it's kind of like, look at, I could do chain rule here. I did outside function, 2x to the 5, 10x to the 4th. What's the derivative of x times 1? So I'm doing chain rule every time. really, but we don't write the times 1, you know? The derivative of x to the 4th is 4x cubed times the derivative of x, which is the base innermost part, times 1. So we just don't write it. Does that make sense? Yeah. Okay. All right. So now, finally, what we need to do, remember, what we're looking for is this, which is y prime. So I need now to solve for y prime. And this isn't hard at all, just regular algebraic manipulation. So I am going to just get all the terms that do not have y prime in them. So this is the terms that have y prime. I'm going to get these terms over to the other side of the equation. So I'm going to put x to the 4, y prime, plus 5y to the 4, y prime. And I'm going to do minus 10x to the 4 minus 4x cubed y. Why do I do that? Because I have a common factor of y prime on this side now. So those two terms, I can remove a common factor, which is the y prime that I'm looking for. Remove that, and I get x to the 4th plus 5y to the 4th equals negative 10x to the 4th minus 4x cubed y. I'm very, very close now. I just divide both sides by my expression here that's multiplied by y prime, and I get y prime equals x to the 4th minus 4x cubed y all over x to the 4th plus 5y to the 4th. And if there's any factoring you can do, you should. Y prime. And of course, I see some factoring here. I can take out a negative 2x cubed. Take out a negative 2x cubed out of this top expression. Oh, that just disappeared. Are you kidding me? Come on, computer. Keep up with me here today. So what's left over is going to be a positive 5x. That's going to be a positive 2y. Okay, if I'm lucid here this morning. And this is x to the 4th plus 5y to the 4th. Don't have to factor that. There's no common factors. Just focus on the common factors. And if there's any factors that you can eliminate now or divide out, that's when you further simplify. But let's just pause and look that over. So if you were doing this on your own, you would go back to the very first step and you would just double check each thing, each term. Let's just see. So in the this is from your textbook, and they stopped. Yeah, they stopped up here. They factored a negative out, but they didn't factor the 2x cubed out. Not sure why. But anyways, so this is the preferred simplified answer there. Okay. So check that out. We got x and y over there, but we don't have any more y primes on the right side. We have y prime just on the left side. That's what we want to solve for. Good? Nice. Any questions? All right. Here's your turn. Yay. Your turn to do this one. Go ahead and use implicit differentiation to find the derivative of this one right here. All right, hopefully you've had a chance to give this one a go here. So let's just highlight the solution here. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared times, chain rule, y prime. Not preferred variable, so you're going to have to multiply by y prime at the end, right? It's not the preferred variable. It's not times 1 at the end. It's times y prime at the end. Just remember that. We'll separate this as a product. So the derivative of the first is 6 times the second, y, plus 6x times the derivative of the second, which is y prime. Okay. So what I'll do now, again, is I need to get the y prime terms together. So I'm going to bring this over to the other side. I'm going to bring this around to the right side to get this expression here. I factor a y prime out, and isolate for that y prime. I notice that I have a common factor, top and bottom. I will remove a 3 out of the top and the bottom, and then those divide out to be 1, and this should be your final answer there, circled. Okay, thoughts on that? How's that? How you feeling about that? On a scale of 1 to 5, 1 is, I don't get this at all. You're speaking like Russian or something. I don't understand this. Unless you're Russian and you speak Russian, You don't understand. And 5 is like, this is easy. I could teach this tomorrow to someone. No problem. Okay, let's see. Show me some fingers. All right, I'm seeing a lot of fingers. Okay, I'm seeing some fluttering fingers. Don't know what that means. Not sure. Your processor is stuck on the wheels going around. I don't know. Okay, all right, well, hey, that's great. We have time for maybe one more quick one. So I'll do one more quick one, and then I'll give you your assignment today. So, okay, so this one here, again, might want to rewrite this as x to the 1/2 plus y to the 1/2 equals 1. It's going to be 1/2 x to the negative 1/2 plus 1/2 y to the negative 1/2 y prime equals 0. I'm going to solve for y prime. So I'll retain this here. Negative 1/2 x to the negative 1/2. Okay. I can divide by 1/2 both sides. I got a 1/2 is pretty common there, so I can take out the 1/2 from both sides. And I will isolate the y prime. I'm going to do x to the negative 1/2. So x to the negative 1/2 over y to the negative 1/2. And this is going to equal y to the positive 1/2 over x to the positive 1/2 if we flip those around, which is root y over root x. Now let's just see. And with a negative here as well that I forgot to write down. So there's your answer there for G. That was a really quick one at the end there. You heard the bell. So that's that one. Here's your assignment right here for 2.7. Hi. How's it going? Not good, not bad. Solid mediocre.